Welcome to Chapter 3, Section 2. In our last chapter, we talked about Dalton's atomic theory and some of the laws that have governed the way scientists um, thought about atoms. And so now let's just imagine along our historical jaunt here, we're about at the 1850s. And this is when scientists started to discover the subatomic particles. And all I mean by subatomic particles is smaller than an atom. Okay, remember, up till this time, Dalton had said that atoms are these things, and you can't get any smaller than that. That's all there is. Okay, but a guy by the name of J.J. Thomson did some experiments that proved that atoms were indeed made of something else. Oops. Let me get this one right here. Okay, so the guy that kind of started it was J.J. Thomson, and he used what's called a cathode ray tube, or sometimes it was called a Crookes tube. And I've got a picture of one right down here. Okay, and what it is they've got this tube right here, and what Thomson did is he took out all of the air. So basically, it was a vacuum, hooked it up right there that you can see an electrode there, an electrode there, and then pumped it full of energy. Imagine what happened. Well, what he found was that when they pumped an electric current through it, a beam was glowing. And not only was it glowing, but it was glowing from this negative end right here. And you can kind of see that here. You can see this beam right there glowing. And then they've got some phosphorescence on the screen here that kind of shows it, kind of gives a little light. But the beam was flowing from the negative end. Right? So now Thomson has figured, well, there's no air in there, so somehow this negative beam must be coming from the cathode itself. All right, that's kind of the next thing. So since the cathode is the negative end right there, oops. Since the cathode is the negative end right here, the idea is that we've got a negative beam. Okay, and then further on, the idea is, well, let's prove that this beam is negative. So what could they do? Well, what kind of things can affect negatives? Well, positives, right? So you can imagine maybe he held up a negative beam or a positive beam and it bent, or he tried a magnetic field. So what would happen is in this beam, just imagine holding a magnet right here, and that would cause the beam to either go up or to go down. Or if he held a negative thing right here, that would cause the beam to go up. So both a magnet and electric field deflected the beam. So now we're kind of going, wow, we've got these things that are from atoms and they're negatively charged. And so they're starting to look at Dalton's idea of atoms being these whole things as not quite holding up. So then the next step in the whole process was this example of putting a paddle wheel in the beam. And that's what we've got right down here. You can see this Crookes tube here, and there's a paddle wheel. And imagine the beam going right there. And what happened when that paddle wheel was placed in the beam is the paddle wheel moved. Now, the only way that the paddle wheel could move is if it was hit by something, kind of like throwing little balls at it. And so the fact that the beam moved the paddle wheel gave them another very important piece of information, and that is that these tiny particles must weigh something. They must have mass. Now, it's not very much. If you're into numbers, it's 9.1 times 10 to the minus 31 kilograms. That's pretty teeny tiny. But it still was a mass. They ended up calculating that by being able to bend the beam a certain way with a certain amount of electricity. Stuff that we're not going to deal with right now. So the paddle wheels were moved, and that was starting to lead lead him to thinking some things. And so the idea was, well, let's put another metal here in this cathode. All right. So let's say that this cathode right here, it's maybe the first time they used iron, okay, and now this time they used tin, or the next time they used aluminum. Okay? But every time the results were exactly the same. So now the idea is, hey, not only is this beam producing a negative thing, but it doesn't matter what we put there, we get the same exact results. So therefore the idea is that, hey, atoms are made of some negative things. And again, I kind of already alluded to the weight, but through experiments by the guy by the name of Millikan, they figured out the exact mass of an electron, and it's right there. It's this number I have right here, pretty teeny tiny. And so the idea is that, wow, we've got to change Dalton's laws, or at least Dalton's atomic theory, because he's showing that atoms have these negative parts. But wait a minute. Here's the part that's confusing. We know that atoms are neutral. Well, if atoms have some kind of negative thing, what must also be present? A positive thing, right? And so that kind of led to the idea that, wait, there must be some kind of positive thing. So atoms we know are neutral, and there must be some other subatomic particle that has a positive charge. And that took another, 40 years or so to discover. So let's look at the kind of model that Thomson had. They called it the plum pudding model. And I imagine because it was British, and plum pudding is a British dessert. I kind of like to think of it as the blueberry muffin model. Okay, so what we have here is we have this area of positiveness. You can see the circle there, right? And then interspaced in the area of positiveness are these negative charges. Now, if you want to apply that to the model, imagine that the positiveness is the muffin itself, and that the electrons are actually the blueberries. Okay, so that was the idea of the model around the mid 1800s, and then and it stayed like that for a while until a man by the name of Rutherford came up with an experiment that again changed the model of the atom. And so let's look at Rutherford's experiment. Now Rutherford was a physicist, and he had a number of students, and he wanted to conduct this experiment, but it's a pretty interesting little experiment here. And the basic way it works, and by the way, let me write this out. His experiment was called the gold foil experiment. For obvious reasons, look at the gold foil right down here. Okay, but this is what he did. Okay, he put this radioactive material in here. I believe it was polonium. Put some polonium here that gave off alpha particles. That's an alpha sign. Okay, and basically an alpha particle is a helium nucleus. Okay, so we're talking 2 protons and 2 neutrons. Pretty darn heavy, coming at very, very high speeds. And so the idea was, well, let's take some alpha particles, shoot them at a gold foil, and see what happens. Now, Rutherford felt that since he knew the beam was high in energy, and the gold foil was very thin, and if you've ever seen gold leaf on a book, you know what I'm talking about. It's really thin. He felt the beam would go all the way through. But what in fact was shocking to him and all of his colleagues is that some of the beams actually bounced off, and a few of them bounced back. So you can kind of see the ones over here that bounced off, and then the ones that bounced back. Right? He's got a famous quote, by the way, that says, it was like firing a cannon at tissue paper and having the shell come back and hit you. Absolutely shocked that this would happen because he just felt that the particles would go right through. And so this was a real big revelation because it kind of gave the idea that, wait, if I'm shooting this thing right here, this nucleus, by the way, which had a positive charge, and it's bouncing back every once in a while, it must be hitting something that's very small and also positively charged. And that was the idea. So now, the blueberry muffin model, this one over here, it doesn't work anymore because most of the particles went right through. And they were positive particles. Well, if they hit any of this area that's all positive, they would have bounced back right away. So he knew that wasn't the case. And so later on, by using, oops, I hate when I do that. Later on, by measuring the deflected angles and the number of particles that were hitting, they figured out the size of what he called was the nucleus of the atom. It was about 1/10,000th of the whole atom. Now there's a lot of analogies about what's the relative size of a nucleus to the first electron, and we'll go into that later. But basically, the nucleus was very, very small. So you can imagine a model that would look it would look something like this, where we have a nucleus at the very center of this atom, and the rest of it here would be the first electron out here. Okay, there would be our electrons way out here. And so that's the idea. So the model completely changed. We went from Dalton, that was this, these unbreakable spheres. Then we went to Thomson, that was this plum pudding model. And now we have this Rutherford model that was more like, no, there's this teeny tiny positive region in the center surrounded by the rest of the atom. Okay, so what else is there from this, basically? Well, we knew that the charge of a proton was calculated to be opposite of the electron. That helped us understand that, okay, now that the atom is neutral, and this makes sense because we've got these things that are positive and these things that are negative. And then later experiments also showed that the protons were about 2,000 times the weight of the electron. And so when I told you that electrons were like 10 to the 31st, negative 31st, we're talking about 10 to the negative 28th kilograms. Still teeny tiny, but quite a big deal. And so the fact that it is 2,000 times bigger just leads us to understand that when we're talking about the weights of the atoms, we're mostly worried about the protons and the neutrons. Okay. So where are we at right now? Now we've got this model, and I like to call this the Jimmy Neutron model because my kids have watched that show quite a bit, of this center nucleus, and this center right here, nucleus, and then these electrons going around. And if we're really going to be true to the Rutherford model, that nucleus would have to be a lot smaller. All right. But at this point, now we're talking maybe the early 1900s. At this point, there's still some unanswered questions. What about the extra mass? For example, they were kind of getting the idea of what a proton weighed, and they knew the weight roughly of a sample. And if you added all the weights of the protons, and even the electrons for that matter, it didn't account for all the mass. And so that was one of those things that kind of led scientists to look for something else. And about 30 years later, Irene Juliet Curie discovered a beam that could go through almost anything. And then a guy by the name of James Chadwick took this beam and found out that it wasn't deflected by an electrical charge, wasn't deflected by a magnetic field, and he eventually came up with the idea of the neutron. And so that's kind of where we stand at this point. Protons and neutrons. So our model for right now is this nucleus right here. Oops. with protons and neutrons. Okay, and then around the nucleus we have our electrons. All right, and so there's just a little bit of history of where we came from Dalton through Thomson and eventually to Rutherford. So Goldfoil experiment is super important. All the things that Thomson did to discover the electron are super important. And I'll see you in class soon, and we'll talk about this further.